There is a number that most scientists don't want to mention in press conferences about space exploration. This is a devastatingly large number that when you truly understand it, all illusions of becoming an intergalactic civilization collapse like a house of cards. That number is 2.5 million light-years. This is the distance to Andromeda, our nearest neighboring galaxy. To help you truly understand what this means, let me put it into a different perspective. If the Milky Way were the size of a €1 coin in your hand, Andromeda would be another coin nearly 3 meters away. Sounds manageable, right? But now, scale that up to reality. Each millimeter of that coin represents 1,000 light-years of empty, deathly cold space. The Voyager probe, our fastest and most distant man-made object, has been traveling for 47 years at over 60,000 kilometers per hour. During that entire time, it has barely left our solar system. It hasn't even truly reached deep interstellar space. If we aimed Voyager straight for Proxima Centauri, our nearest star, it would take 73,000 years to get there. 73,000 years to travel 4.25 light-years. Now, take a deep breath and do the math for Andromeda. With Voyager's technology, we would need about 1,800,000,005 years to reach the nearest galaxy. 1,800,000,005 years. By the time we arrived, if anything arrived at all, the sun would have expanded its atmosphere and evaporated the oceans on Earth. Our planet would be a scorched desert, or perhaps wouldn't even exist anymore. Humanity would be a forgotten fossil, if there was anything left to remember. But perhaps you think Voyager is old technology, that we could go faster. And technically, you'd be right. The most optimistic proposals for advanced spacecraft, using solar sails or fusion propulsion, could reach 10 to 20% of the speed of light, impressive numbers compared to what we have now. At 20% the speed of light, we could reach Andromeda in about 12.5 million years. From the time the first hominins started walking upright in Africa until today, only 7 million years have passed. The entire history of humanity, from the first stone tools to smartphones and spacecraft, has taken place in a tiny fraction of that time, and we're only talking about a one-way trip. The reality is that the space between galaxies is not like the space between planets or even between stars. It is an abyss of a scale that our brains, which evolved to hunt on the African savanna and pick fruit from trees, simply cannot process. When astronomers say space is empty, they don't mean a room without furniture. They are talking about voids where you could travel for millions of years without finding anything. Not one speck of dust, not one stray atom, nothing but perfect darkness and the absolute cold of 2.7 degrees above absolute zero. To make things more complicated, that abyss is not stationary. It's not a calm ocean we can cross with infinite patience. Intergalactic space is constantly expanding, stretching like a rubber band, being pulled relentlessly. Every second that passes, Andromeda and we should be farther apart. Except the mutual gravity between these two galaxies is so strong that we are, in fact, getting closer. But we'll talk about that paradox later. Because what's important now is to understand that we live in a universe where distances are not just colossal, but actively resist any attempt to cross them. Think about this. Light, traveling at 300,000 kilometers per second, takes 2.5 million years to get from Andromeda to your eyes. Light has no mass. It needs no fuel. It doesn't get tired. It doesn't age. It is literally the fastest thing that can exist in the universe, according to the laws of physics. And yet it still needs 2.5 million years to complete that journey. When you look at Andromeda in the night sky, You are seeing it as it was at a time when our ancestors, the Australopithecus, were just beginning to make the first tools in Africa. Now, imagine trying to send a ship carrying humans, with all the necessary infrastructure to keep them alive: food, water, air, radiation shielding, redundant life support systems, fuel for course corrections, repair equipment, living quarters, recycling systems. The weight of all that would multiply exponentially. The energy needed to achieve any significant speed. We're not talking about small differences. We're talking about each extra kilogram requiring an astronomical amount of additional energy. Scientists at NASA and ESA have calculated theoretical missions to the nearest stars, not to galaxies, but just to the stars in our immediate neighborhood, and the numbers are sobering. Project Daedalus from the 60s calculated that a robotic mission to Barnard's star, 6 light-years away, would require 54,000 tons of helium-3 fusion fuel, 54,000 tons for a robotic trip to a relatively close star. Now multiply that by the needs of a manned mission to a distant galaxy, and the numbers become literally astronomical, in the most literal sense of the word. There is another aspect of this problem that is rarely discussed. That is navigation at interstellar distances, and even more so at intergalactic distances. Navigational errors are magnified exponentially. A mistake of just 1,000th of a degree in your initial trajectory could cause you to miss your target by millions of light years. And there is no GPS in intergalactic space. There are no reference satellites, no signals you can use to correct your course in real time. You would have to navigate by stars whose positions will have changed by the time you reach your destination, using calculations that must predict the positions of objects millions of years in the future. Computer simulations of hypothetical intergalactic journeys show another frightening problem: gravitational drift. Although the space between galaxies is mostly empty, it is not completely empty. There is dark matter, even though we can't see it. There are weak but present gravitational fields. Over a journey of millions of years, these tiny gravitational effects would accumulate, deflecting your trajectory in ways that are impossible to predict accurately. It's like trying to make a perfect pool shot on a table the size of a continent with the ball rolling for 1 million years. The statistical probability of hitting the target is practically zero. And then there's the time factor. Even if we solved all the technical problems, even if we built a ship that could travel at 20% the speed of light, even if we could keep generations of humans alive for millions of years, what would we find when we got there? Andromeda would no longer be where we see it now. It would have moved. The stars within it would have been born and died. Civilizations that might have existed there could have risen and fallen 1,000 times. We would be chasing a ghost, an illusion of ancient light, trying to reach something that ceased to exist in that form millions of years ago. The harsh reality is that intergalactic distances are not just large, they are immeasurably vast, rendering any conceivable technology a useless toy. No matter how advanced we become, no matter what we discover, no matter how long we survive as a species, the abyss between galaxies remains endless. For all practical purposes, this is our first encounter with the bars of our cosmic cage. The distance between galaxies is not an obstacle we can overcome. With enough ingenuity or determination, it is an absolute wall, built by the very fundamental geometry of the universe. And this is just the first of many walls we will discover, because even if we could solve the problem of distance, even if we could make light years irrelevant, there are more fundamental barriers waiting for us. Barriers that make distance seem like our smallest problem. The question is no longer how we will get to other galaxies. The question is, why is the universe designed in a way that ensures we never will? Intergalactic distance is daunting, but at least it's a problem we can conceptually imagine solving, given enough time. maybe with generation ships, maybe with hibernation, maybe with something we haven't invented yet. But there is a much more fundamental barrier, much more absolute, that shatters even the most optimistic fantasies. A barrier that cannot be overcome with ingenuity, patience, or future technology. That barrier is energy, specifically the amount of energy required to move any object with mass at speeds that make intergalactic travel remotely possible. And when I say amounts of energy, I don't mean a lot of energy. I'm talking about obscene amounts of energy, making all of humanity's energy reserves seem like the spark from a lighter compared to the sun. Let's start with a concrete number that will help you understand the severity of the problem to accelerate a spaceship weighing about 1,000 tons, approximately the weight of the International Space Station ISS. Up to 50% of the speed of light, you would need about 1,300,000,000 terajoules of energy. To put this into perspective, that is more energy than all the electricity ever generated. By all of humanity in their entire history, all the energy from every power plant, every nuclear plant, every solar panel, every windmill, every burning of coal oil and gas. Since we discovered fire, all of that combined would not be enough to accelerate a single ship the size of the ISS to half the speed of light, and that's just to accelerate. You still need to decelerate when you arrive, which requires an exactly equal amount of energy. So, double that number. And remember, we're talking about reaching only 50% of the speed of light, which means the trip to Andromeda would still take 5 million years, but the problem gets exponentially worse as you try to go faster. This is due to one of the most beautiful and cruel equations in physics, the relativistic kinetic energy equation. At low speeds, energy increases linearly. With speed, you double the speed. Energy increases fourfold. But as you approach the speed of light, this relationship becomes exponential, then super-exponential, and finally asymptotic. In other words, the closer you get to the speed of light, the more energy you need, and that amount increases to infinity. To reach 90% of the speed of light, you would need double the energy compared to reaching 50% to reach 99%. You need 10 times more. To reach 99.9%, you need 20 times more energy than the 99% level, and to reach 99.99%. The numbers become literally astronomical. We're talking about amounts of energy equivalent to the total output of the sun. For many years, scientists have calculated that to accelerate a 1,000-ton ship to 99.99% of the speed of light, you would need about 4,200,000,000 tons of perfect fuel in a perfect reaction. Converting mass into energy, 4,200,000,000 tons, for reference, all of humanity, consumes about 14 billion tons of oil, equivalent per year. You would need nearly 1/3 of the annual energy consumption of the entire human civilization, but not in the form of oil or coal, but in the form of perfect fuel with 100% mass-to-energy conversion efficiency. And here's the problem, that perfect fuel doesn't exist. The most efficient reaction we know of is matter-antimatter annihilation. When 1 kilogram of matter meets 1 kilogram of antimatter, they annihilate each other, turning into pure energy. According to Einstein's famous equation, E equals mc, squared in theory, it's perfect. Each gram of mass is converted into about 90 petajoules of energy, but antimatter doesn't grow on trees. You have to make it, and making it requires an amount of energy, exactly equivalent to the amount of energy that it will release upon annihilation. It's like filling a gas tank using the very energy you hope to get from that gasoline. You end up with a net zero. Worse still, our current methods for producing antimatter are currently extremely inefficient. For every 1 million units of energy we invest, we only get a few units of usable antimatter. The rest is lost as heat, radiation, and secondary processes CERN. The world's most powerful particle accelerator can produce about 10 million antiprotons per minute. On its best days, which sounds impressive until you do the math, you would need CERN to operate continuously for about 100 million years to produce just 1 gram of antimatter on gram. And remember, we need billions of tons, even if we could miraculously solve the production problem storing antimatter. Is another complete nightmare. Antimatter cannot touch ordinary matter, or it will annihilate instantly. You need extremely strong magnetic fields to keep it suspended in a perfect vacuum. Those magnetic fields require constant energy. And if something goes wrong, if there's a power failure, if a micrometeorite punctures your container, all your antimatter will annihilate instantly in an explosion that would make thermonuclear bombs seem tiny. But let's assume we solve all those problems. Assume we find a way to produce and store large amounts of antimatter efficiently. We still face a fundamental problem: the Tsiolkovsky rocket equation. This equation, formulated in the early 20th century, describes a brutal truth about space travel. The vast majority of your ship's weight is fuel, and that extra fuel requires more fuel to accelerate it, and even more fuel to accelerate that fuel, and so on in a vicious cycle. For an intergalactic journey, the fuel-to-payload ratio becomes absurd. Some calculations suggest a ratio of 1 million to 1 for every kilogram of payload equipment, crew, food, water. You would need 1 million kilograms of fuel. And those 1 million kilograms also need to be accelerated, which requires more energy and in turn requires more fuel. It's a self-feeding paradox that collapses. Mathematically, engineers have proposed creative solutions. For example, the Bussard ramjet, which would collect hydrogen from interstellar space and use it as fuel for a continuous nuclear fusion reaction in theory. You would never run out of fuel because you're collecting it as you go, problem solved, right? Not quite. The most recent calculations show that the density of hydrogen in interstellar space is too low. So low that you would need a collector the size of a country to gather a useful amount, and in intergalactic space, where the density is 1,000 times lower. You would need a collector the size of a solar system. The structural forces required to hold such an object together at relativistic speeds would instantly tear it apart. Others have proposed solar sails, pushed by giant lasers from Earth. The idea is the ship carries no fuel. The energy comes from lasers pushing it from home. But the numbers are again brutal to accelerate a reasonably sized ship to relativistic speeds using lasers. You would need a laser system that consumes the total energy output of the sun, literally, and you would need to keep that laser beam perfectly focused on a ship moving away at relativistic speeds for decades or centuries. A targeting error of just a millisecond, and you lose the ship forever. There's also the nuclear bomb proposal. Project Orion from the 60s suggested launching nuclear bombs behind a ship and riding the shockwaves. In theory, it would work. In fact, it's one of the few propulsion proposals that we could actually build with current technology. The problem is, you would need millions of nuclear bombs. Millions. For a trip to the nearest star for an intergalactic journey, you would need more bombs. Nuclear bombs than there are atoms on Earth, which is obviously impossible. Every proposed solution eventually hits the same wall. The energy required for intergalactic travel exceeds the available energy within the system we want to use. It's like trying to bail out the ocean using the ocean's own water. No matter how efficient your pump is, it will never work because the task requires more resources than the system can provide. And this leads us to the most brutal revelation of all. Even if we could build a perfect antimatter engine, even if we could solve every engineering problem, even if we could harness unlimited amounts of energy from the sun or from nuclear fusion, we would still hit an absolute barrier. The speed of light is not just a speed limit. It is an energy limit. As you approach the speed of light, the energy required to accelerate even 1 more gram approaches infinity. Literally infinite. No matter how much energy you have, it will never be enough. to reach the speed of light because the universe has placed an infinite energy wall right at that limit. Physics isn't cruel. Physics is absolute, the laws that allow energy to exist, that allow atoms to exist, that allow you to exist to read these words are the very same laws that ensure you will never be able to accelerate fast enough to make intergalactic travel feasible. This is not a matter of technology, not a matter of time or patience or ingenuity. This is a matter of the fundamental laws of the universe, a barrier that cannot be broken, bent, or dodged. Energy is not an obstacle we can eventually overcome. It is an absolute wall etched into the very fabric of reality, and this wall has an even more devastating consequence that we have yet to discuss, a consequence that makes the problems of distance and energy seem trivial in comparison, because even if we were to solve both, even if we miraculously found a way to travel fast without impossible energy requirements, there would still be a third barrier waiting for us, a barrier that ensures any intergalactic traveler would be condemned to a fate worse than death, absolute and eternal isolation from the rest of humanity. Imagine that we finally succeed. Imagine that we solve the problems of distance and energy with some miraculous future technology. We build a ship that can travel at 90% the speed of light and send it towards Andromeda with a crew of brave explorers. It is the greatest moment in human history. The cameras broadcast live as the ship moves away from Earth, as it crosses the Moon's orbit, as it passes Mars and Jupiter, leaving the solar system and entering the interstellar abyss. And then something happens that no one fully anticipated in the simulations. Something physicists knew would happen, but whose existential implications were never truly discussed publicly. The messages from the ship begin to arrive more sparsely, not because the crew is sending fewer messages, but because each signal takes longer to arrive after 1 year. There is a 1-year delay after 15. The delay is 15. After 100 years, your descendants are receiving messages from people who have been dead for many decades. But this is just the beginning of the problem. The real horror begins when you consider what happens to radio signals at relativistic speeds when an object is moving very fast away from you. The electromagnetic waves it emits get stretched out. This is the famous Doppler effect, the same thing that makes an ambulance siren sound lower-pitched as it moves away. But at near light speeds, this effect does not just change the pitch, it completely destroys the signal. A radio signal sent from a ship moving at 90% the speed of light will suffer an extreme redshift. The frequencies are stretched so much that a signal sent in the FM radio band would arrive at Earth as nearly undetectable extremely low-frequency radio waves, and this gets exponentially worse with speed at 99%. The speed of light. The signals are stretched so much that they become practically undetectable even by our most sensitive radio telescopes. But the Doppler effect is just the first layer of this communication hell. There is something far worse in store-time dilation. Einstein proved that time is not absolute. It passes at different rates. Depending on how fast you are moving at normal speeds, this difference is tiny and negligible. But at relativistic speeds, the difference becomes dramatically existentially devastating. For a ship moving at 90% the speed of light, for every 1 year that passes for the crew, about 2.35 years pass on Earth sounds manageable, right? A discrepancy you can account for in your calculations, but at 99% the speed of light, the ratio is 1 to 7. For every 1 year for the crew. 7 years pass on Earth at 99.9%. It is 1 to 22. At 99.99%, it is 1 to 70. Now think about what this means for communication. Imagine you are part of the crew and you send a message to Earth saying, "Everything is fine. We have completed the first year of our journey." That message travels at the speed of light back to Earth. But while it is in transit, Earth continues to age much, much faster than you. By the time your message about completing the first year reaches Earth, decades have passed. Your children are old. Your grandchildren have their own grandchildren. The world you left behind no longer exists. And when Earth replies to your message, their answer takes decades to reach you, but from your subjective sense of time, it seems as if Earth has simply stopped replying. The messages arrive more and more infrequently, increasingly out of sync with your reality. The replies you do receive are to questions you asked months ago according to your clock, but they were sent decades ago by Earth's clock, a study published in 2024 by physicists from Oxford University modeled this exact scenario and came to a devastating conclusion. At the speeds required for viable intergalactic travel, coherent two-way communication becomes physically impossible. Not difficult, not complex, but impossible. The time desynchronization is so severe that any attempt at a conversation collapses into a chaotic mess, with messages arriving out of order, devoid of context, with references to events that have not happened yet, or happened so long ago they are no longer relevant. Imagine trying to have a conversation where every word you speak takes 1 year to reach the other person, and their reply takes another year to get back to you. But on top of that, time is passing at different rates for both of you. It is like trying to play chess by mail. If the letters arrived randomly out of order, and the other person aged 15 years for every move you make, but there is an even deeper layer of horror to this. It is not just that communication is difficult or delayed. It is that maintaining a coherent signal eventually becomes literally impossible. Electromagnetic signals lose energy as they travel. They get scattered, weakened, and corrupted by cosmic noise. At interstellar distances, you need enormous antennas and immense transmission power just to send simple messages. At intergalactic distances, the amount of energy needed to send a detectable signal becomes prohibitive. Scientists calculate that to send a simple radio message from Andromeda to Earth that could be detected by our most powerful radio telescopes, you would need a planet-sized antenna, transmitting with a power output equivalent to several stars, and that is just to send something, equivalent to a few words to send video. Audio or complex scientific data, you would basically need energy sources so vast. You would need a Type 2 civilization on the Kardashev scale, a civilization that can harness the entire energy output of its star, and this assumes both ends of the communication are stationary. But remember, the ship is moving at relativistic speeds. The Doppler effect is distorting all the frequencies. Time dilation is desynchronizing all the clocks, and the distance is constantly increasing. Every second, the ship is millions of kilometers farther away. Every day, tens of billions of kilometers farther. Every year, distances that defy comprehension. There is also another rarely mentioned phenomenon, the relativistic aberration of light. At near light speeds, your perception of the universe fundamentally changes. The stars in front of you seem to converge into a single bright point, while the stars behind you disappear. The entire sky becomes distorted, and the signals you receive from Earth do not arrive from where you would expect. They are angularly shifted due to your incredible speed. You have to constantly calculate where to point your antenna, not at where you see Earth, but at where Earth will be when your signal arrives, compensating for both your own motion and time dilation. The complexity of maintaining communication under these conditions is not just a technical problem. It is an existential one. You are trying to maintain a connection with a world aging at a different rate, separated by a gulf so vast that signals take years, decades, or centuries to travel, where every message you send is a time capsule from a version of yourself that technically no longer exists by the time the message arrives. Psychologists who have studied extreme isolation in Antarctica, on nuclear submarines, and in space simulation missions all agree on one thing: humans need regular social connection to maintain their sanity. Not just occasionally, but regularly, ideally daily, when that connection is delayed for too long. When replies take weeks instead of seconds, the human psyche begins to fracture. People develop depression, anxiety, and psychosis. Now imagine that replies do not take weeks but years or decades. That every message you send is essentially a letter thrown into the void with no real hope of a meaningful response. That each passing day pushes you further away from the only species you can truly communicate with. That you are condemned to spend the rest of your life and the lives of your children, and the lives of your children's children in a complete isolation that no human being in history has ever experienced. This is not exploration. This is exile. This is a voluntary exile, and a loneliness so profound it becomes a form of living death. You will still live. Still think, feel, exist, but you will be completely and irrevocably cut off from everything that makes human life meaningful. No real-time conversations. No love shared in the moment. No ability to comfort the grieving or celebrate with the triumphant. And this is the cruelest paradox of all. The very speed that makes the journey possible is what makes connection impossible to move fast enough to make galactic travel feasible. Within a lifetime, you need to go so fast that communication breaks down completely. You cannot have both. It is physically impossible. You can reach another galaxy, or you can stay in touch with home, but you cannot do both. The universe forces you to choose, and both options are variations of tragedy. Galactic travelers will not be explorers. They will be ghosts. Entities trapped between worlds, unable to return to where they left, nor truly belong to where they are trying to go. They will wander the abyss for generations, sending messages that no one answers in time, receiving echoes from a long-dead world, condemned to endure a form of existence that no conscious being should ever experience. And this, cosmic loneliness, is not the only problem travelers must face, because while they drift in that absolute silence while Earth ages at a different rate and communications vanish into cosmic noise, the universe itself is actively working against them in a way that makes all previous problems seem trivial. An invisible, unstoppable force ensures that for every second they spend traveling, their destination moves away faster than they are approaching it. There is a force in the universe that few truly understand, a force so strange and counterintuitive that, when it was first discovered, even the world's best physicists refused to believe in it. A force that neither pushes nor pulls, has no identifiable source, cannot be blocked or dodged. A force that at this very moment is pushing every galaxy away from every other galaxy at an ever-increasing speed. That force is the expansion of space itself. And in 1929, astronomer Edwin Hubble made a discovery that would forever change our understanding of the universe. He observed that almost all distant galaxies are moving away from us, and the strangest thing of all was, the farther away a galaxy is, the faster it moves. It is not that galaxies are moving through space, but that the very space between us and them is expanding, stretching like a cosmic rubber band. Being pulled relentlessly, the relationship he discovered is now known as the Hubble-Lemaitre law. In honor of Hubble and the priest Georges Lemaitre, who first proposed the idea mathematically, this law is deceptively simple. For every 3.26 million 5 light-years of distance, galaxies move away about 70 kilometers per second faster. 70 kilometers per second per megaparsec in astronomical terms sounds like a small number until you start doing the math. Andromeda, at 2.5 million light-years away, should be moving away from us at about 54 kilometers per second due to expansion. In fact, it is approaching us at about 110 kilometers per second, because the mutual gravity between our two galaxies is strong enough to overcome the expansion. We are the exception. Andromeda and the Milky Way are destined to collide in about 4 billion years, but beyond our local group of galaxies, beyond the few dozen galaxies, gravitationally bound to us, the expansion reigns supreme. A galaxy 300 million 5 light-years away is moving away at about 6,000 kilometers per second. A galaxy 3 billion light-years away is moving away at 65,000 kilometers per second. And this is where everything completely breaks down at a distance of about 14 billion light-years. Galaxies are moving away from us. At the speed of light, read that again, because it is important at a distance of 14 billion light-years. Roughly the size of the observable universe, galaxies are moving away at 300,000 kilometers per second. And beyond that point, they are moving away faster than the speed of light. This does not violate special relativity because the galaxies are not moving through space, faster than light. It is the space between us and them that is expanding, faster than light can traverse it. This is the ultimate cosmic trap. Imagine you are on a giant cosmic treadmill that is constantly accelerating. It does not matter how fast you run. The treadmill moves faster. Eventually, you reach a point where even running at your maximum possible speed, the speed of light, you are still moving backward instead of forward. That is exactly what potential intergalactic travelers face right now. Andromeda is special because it is close enough for gravity to overcome the expansion. But suppose we aim for another galaxy, a more distant one, for example, the Triangulum Galaxy, about 3 million light-years away, or the M87 Galaxy, about 55 million 5 light-years away. For these galaxies, the expansion is actively working against us. The math is brutally and devastatingly simple. If we were to build a ship that could travel at 99.99% of the speed of light, and point it toward a distant galaxy for the entire duration of the trip, the space between us and that galaxy would continue to expand. Every year we travel, the target distance increases not just because of the space we have not crossed yet, but also because new space is being created while we are moving. It is like trying to swim to shore, while a current is pulling you further out to sea, except this current is not just pulling you back. It is also constantly accelerating with every stroke you take. The current gets a little stronger, and there is no way to swim faster, because you are already swimming at the maximum speed. Physics allows a 2022 study from the California Institute of Technology modeled this exact scenario. They calculated that for a galaxy located more than 4,600,000,000 5 light-years away, known as the Hubble horizon, it is physically impossible to reach it no matter what technology you use. Even traveling at the speed of light for the entire current age of the universe, you would never arrive, because the space in between is expanding faster than you can cross it. This means that about 94% of the galaxies in the observable universe are already beyond our reach. Not because they are too far away in the traditional sense, but because space is expanding so fast that we can never even send a beam of light to reach them. They are observable in the sense that we can see the light they emitted billions of years ago. But they are unreachable in the sense that we can never visit them, and it gets worse. The expansion of the universe is not constant. It is accelerating. In 1998, 2 independent teams of astronomers discovered that the universe is not just expanding, but it is expanding faster with each passing year. They won the Nobel Prize in Physics in 2011 for this discovery. This acceleration is attributed to something called dark energy, a mysterious form of energy that permeates all of space and pushes the universe to expand ever faster. The practical consequences of this are terrifying. The reachability horizon is shrinking galaxies that we could theoretically reach today, if we had the technology, will be beyond our reach in 1 billion years. Galaxies that will be beyond our reach in 1 billion years will be beyond our observable horizon in 10 billion years. The reachable universe is shrinking as we speak, slowly disappearing behind a cosmic event horizon that we can never cross. Think about the existential implications of this. There are civilizations in distant galaxies. At this very moment, civilizations perhaps looking up at our night sky, wondering if anyone else is out there, and we are here wondering the same about them. But due to cosmic expansion, we will never meet, never exchange signals, never share knowledge. We are permanently isolated not by choice or lack of technology, but by the fundamental fabric of space-time. And this applies even to the galaxies within our current theoretical reach. Andromeda, which we can reach because gravity overcomes expansion, is a rare exception. For almost any other galaxy, even those within a few 100 million light-years, the expansion means the trip will take much longer than the current distance suggests, because you would be chasing a target, constantly moving away. Imagine aiming for a galaxy 500,000,005 light-years away. With a ship moving at 99.99% the speed of light, just calculating the travel time without considering expansion, you would need about 500,000,005 years. But during those 500,000,005 years, space has expanded. The target galaxy is now about 600,000,005 light-years away. You need to travel another 100,000,005 years. But during that 100,000,005 years, it expands even more. This is a race you can never win, because the finish line moves away, faster than you can run. Mathematicians call this an asymptote. You get closer to your goal, but never quite reach it. It's like trying to touch the horizon. You walk towards it, and it always seems to be the same distance away, always out of reach, always beyond your next step. And then there's the even darker reality of accelerating expansion. Cosmologists predict that in about 100 billion years, due to the continuous acceleration of expansion, all galaxies outside our local group will disappear beyond the cosmic horizon. Their light will never reach us. They will vanish from the night sky as if they never existed. Future civilizations in our galaxy will look up at the sky and see only darkness. They will have no way of knowing that there was once a larger universe, filled with billions of other galaxies. This is perhaps the most profound form of cosmic loneliness imaginable. A place where intelligent life is bound to arise. Look out into the universe and be permanently isolated from any other intelligent life. By forces it cannot control, overcome, or even defy the universe is designed. By the sheer randomness of its fundamental laws, to keep civilizations isolated on ever-shrinking cosmic islands. But here's the final paradox. Even if we could somehow overcome the expansion, even if we found a way to move faster than the speed at which space expands, we would still run into the barriers that we've already discussed. The energy is still impossible. The distances are still insurmountable. Communication is still unfeasible. The expansion of the universe isn't the only problem. It's simply another nail in the coffin of intergalactic dreams. Another fundamental law says no in the most absolute way possible. And this law has a silent accomplice, another aspect of physics that ensures our confinement. An accomplice that has nothing to do with distance or energy or cosmic expansion. An accomplice that lies within the very equations describing how time, space, and speed work. Einstein's equations that, when you fully understand them, reveal that even in a non-expanding universe, even with infinite energy, we would still be prisoners of our own galaxy, for reasons that are perhaps the most fundamental of all. In 1905, a 26-year-old employee of the Swiss Patent Office published a paper that would forever change our understanding of the universe. Albert Einstein, a name we all now know, proposed something so radical, so counterintuitive, that even today, more than 100 years later, our minds still struggle to fully accept it. He proposed that time is not absolute, that space is not fixed, that both are malleable, flexible, dependent on the observer, and, most importantly for our discussion, that nothing with mass can ever reach the speed of light. This last statement was not a suggestion, not a technological limit we could overcome with enough ingenuity. It is a fundamental law of the universe as inviolable as the conservation of energy, or the fact that 2 + 2 = 4. And this law has devastating consequences. For any civilization dreaming of intergalactic travel, the core of the problem lies in one equation, known as the Lorentz factor, represented by the Greek letter gamma. This equation describes how time, mass, and length change as you approach the speed of light at normal speeds. The Lorentz factor is practically 1, meaning there are no noticeable effects your car moving at 100 kilometers per hour experiences. Relativistic effects so small they are completely irrelevant. But as you get closer to the speed of light, the Lorentz factor starts to increase at 50% the speed of light. It's approximately 1.15. This means that your clock runs about 15% slower than the clock of someone standing still. Doesn't sound too dramatic, right? But watch what happens as you accelerate further at 80% the speed of light. The factor is 1.67 at 90%, it's 2.3 at 95%. It's 3.2 at 99%, it's 7.1. You can already see the trend. The numbers start to increase faster and faster at 99.9%, the speed of light. The Lorentz factor is 22.4 at 99.99%. It's 70.7. And here is the killer problem for intergalactic travel to be feasible. Within a human lifetime, you need enormous Lorentz factors. Andromeda is 2,500,000 light-years away. If you travel at 50% the speed of light, it would take you 5 million years Earth time useless even at 99% the speed of light. It's still about 2,500,000 years Earth time, although for you it would be about 350,000 years. Thanks to time dilation, still completely unfeasible to reduce the travel time to something remotely manageable. Say 100 years of subjective time for the crew. You would need a Lorentz factor of about 25,000. This corresponds to a speed of 99.998%, the speed of light. And this is where relativistic physics hammers home the barrier. The energy required to reach that speed is completely prohibitive. Remember the relativistic kinetic energy equation at low speeds. Energy is simply 1. Half mass times velocity squared. Simple, linear, manageable, but at relativistic speeds. The equation transforms. Relativistic kinetic energy is mass times c squared, times the Lorentz factor minus 1, and when the Lorentz factor is 25,000, you are multiplying your ship's mass. By 25,000 times the speed of light squared, the numbers become obscene for a 1,000-ton ship. The energy required to reach a Lorentz factor of 25,000 is about 2.2 times 10 to the power of 24 joules, to put this into perspective. That is approximately the energy the sun emits in 2 full weeks. You would need to capture the entire energy output of the sun for 2 weeks and focus it perfectly to accelerate your ship, and that's just to accelerate. You need an equivalent amount to decelerate, and this assumes perfect efficiency, a physical impossibility in reality. With the efficiency we could possibly achieve, you would probably need 100 times that energy. We are talking about the total output of the sun for nearly 3 years for a single ship, a single trip. But even if we could magically solve the energy problem, relativity still has other unpleasant surprises waiting for us. One of the most disturbing is the twin paradox amplified on an intergalactic scale. You know, the basic version 1 twin travels into space at relativistic speeds while the other stays on Earth. When the traveler returns, they have aged less than the twin at home. It's a real effect. Experimentally verified thousands of times now. Amplify this to an intergalactic journey. Imagine you depart for Andromeda with a Lorentz factor of 25,000 for you. The trip takes 100 years. You live a lifetime of exploration on the journey. Maybe you have children, grandchildren even. Great-grandchildren. Finally, you decide to return home another century. Subjective time. A total of 200 years for you. But when you return to Earth, 5 million years have passed. 5 million years, the civilization you knew no longer exists. The language you speak is incomprehensible. Your friends, your family, your entire human species as you knew it all, vanished millions of years ago. The continents have shifted. Species have evolved. The Earth you left is literally an alien world. There is no way home now. Technically, you return to the same planet, but that planet has changed so much that you might as well be on another world. You are a ghost out of time, a living anachronism, a person completely disconnected from your own time. This isn't speculative science fiction. It is a direct mathematical consequence of the equations of Einstein, which are unavoidable, inescapable, and absolute. There is also the problem of relativistic mass. As you accelerate, your effective mass increases by the Lorentz factor. This doesn't mean that you have more atoms, but that your inertia increases, making further acceleration increasingly difficult. At 99.99% the speed of light, your effective mass is 70 times your rest mass. This means that any force you try to apply to accelerate further must overcome an inertia 70 times greater, and this creates a vicious feedback loop. You need more energy to accelerate further, but as you accelerate, your effective mass increases, which in turn requires more energy to accelerate, which then increases your effective mass even more. It's an exponential curve shooting straight up to infinity. As you approach the speed of light, your effective mass approaches infinity, and the energy required to give you even a small additional acceleration also approaches infinity. This is not a hyperbole. It is a literal mathematical truth at the limit where your velocity approaches c, the speed of light. Your effective mass diverges to infinity. It would take infinite energy to accelerate a massive object to exactly the speed of light. Infinity is not just a very large number, but literal infinity. The universe has placed an infinite energy wall right at that limit, ensuring you can never cross it. And there's more at extremely high relativistic speeds. The universe in front of you begins to behave in strange ways. The photons of the cosmic microwave background radiation, normally harmless at just 2.7 degrees Kelvin, become extremely blue-shifted. So much so that they turn into deadly gamma rays at a Lorentz factor of 25,000. These photons would hit your ship with the energy equivalent of high-energy gamma rays, constantly bombarding you with lethal radiation. Engineers have calculated that you would need shields several meters thick made of dense material just to protect against this radiation. But those shields have mass, and that additional mass requires more energy to accelerate, and more mass for fuel, and more shields to protect that fuel. It's another vicious cycle with no elegant solution. Even the normally invisible and irrelevant interstellar dust becomes a lethal hazard at extremely high relativistic speeds. A single dust particle, the size of a grain of sand, hitting your ship at 99.99%, the speed of light would release the energy, equivalent to several atomic bombs. Every dust particle is a potential catastrophic explosion you would need to constantly detect and avoid them, or have shields so massive and resilient that the extra weight would make the journey impossible. Then there's the problem of relativistic navigation at near light speeds. The stars in front of you appear to concentrate into a single bright circle due to the aberration of light. The stars behind you disappear. Your perception of the entire universe is distorted. Calculating a trajectory becomes incredibly complex because you have to compensate, not just for the target's motion during the trip, but also for the relativistic effects on your perception of space-time itself. And all of this assumes you can accelerate and decelerate gently. But humans can only withstand a certain amount of acceleration before dying about 3 to 4 times Earth's gravity, sustained over a long period to accelerate to 99.99%. The speed of light at 3 Gs of acceleration would take about a year. That sounds manageable. But that 1 year of acceleration requires a massive amount of fuel burning constantly. And then you need another year of deceleration upon arrival, and the same for the return trip. A total of 4 years of acceleration and deceleration. For a single round trip during that entire time, you are burning fuel at a phenomenal rate. Calculations show that for a complete round trip to Andromeda, even with perfect matter-antimatter propulsion, you would need to carry about 99.99% of your ship's mass as fuel. Only 0.01% could be payload crew equipment. Everything else that means to have a 1,000-ton habitat module. You would need a ship with an initial mass of nearly 10 million tons, for reference the largest ship ever built. The supertanker Seawise Giant weighed about 650,000 tons. You would need to build something 15 times larger than the largest ship in human history. Except this thing would have to operate in the vacuum of space, withstand extreme radiation, and burn antimatter with perfect control for years. Relativity isn't cruel. Relativity is completely indifferent. The very equations that beautifully describe how the universe works, that perfectly predict the behavior of everything from subatomic particles to black holes, are the same equations that permanently close the door to intergalactic travel. Not because Einstein said no, but because the mathematical structure of space-time itself says no, and these relativistic barriers assume we can build the ships, generate the energy, and solve all the engineering problems. But there is one final obstacle. That we haven't discussed an obstacle that has nothing to do with physics or math or engineering, an obstacle that lies within ourselves. Our fragile bodies have evolved to thrive on the surface of a specific planet, surrounded by a protective magnetic field, bathed in the radiation of a specific star. Bodies that when you take them out of that perfect environment and launch them into the intergalactic abyss, they simply fall apart. We've talked about impossible distances, prohibitive energy, about broken communication, and about an expanding universe pushing us away from our destination. We've discussed the barriers of relativity, which make time itself an enemy. But there is one final barrier that is perhaps the most intimate, the most personal, the most devastating of all. A barrier that lies not in the stars or in the equations or in the limits of fuel. It lies within our own bodies. Humans have evolved over millions of years. In a very specific environment, the surface of Earth bathed in the radiation of a G-type star, protected by a planetary magnetic field that deflects deadly charged particles surrounded by an atmosphere that filters out the most harmful ultraviolet rays with a precise gravity of 9.8 meters per second squared. Every cell in your body, every biological system, every metabolic process is optimized for these exact conditions. And when you leave that protected environment, when you venture into deep space and especially into the intergalactic abyss, your body begins to break down in ways that are both inevitable and terrifying. Let's start with radiation. On Earth, you are protected by two invisible but absolutely critical shields. Earth's magnetic field deflects most of the solar wind, the charged particles. The sun constantly spews into space. The atmosphere absorbs cosmic rays, the high-energy protons and atomic nuclei that constantly rain down from deep space together. These shields reduce your radiation exposure to a level your body can handle, that your DNA can repair. In interplanetary space, such as on a trip to Mars, you lose the protection of the atmosphere, but you still have some protection from the sun's magnetic field. Radiation exposure increases significantly. Astronauts on the International Space Station receive about 50 to 200 times more radiation than on Earth's surface, enough to significantly increase their cancer risk. But it's manageable for missions lasting a few months in interstellar space. You lose even the protection of the sun's magnetic field. Cosmic rays hit you without a filter, but at least you are still inside the Milky Way galaxy, where the galactic magnetic field provides some minimal protection. NASA studies estimate that a decades-long interstellar journey would expose astronauts to a radiation dose almost guaranteed to cause cancer, but in intergalactic space, all of this disappears. There is no galactic magnetic field to protect you, no heliosphere, nothing but absolute vacuum and unfiltered radiation coming from all directions. Cosmic rays with energies so high, they can penetrate meters of shielding particles that can fragment atomic nuclei in your cells, creating cascades of secondary radiation that are even more damaging. The calculations are brutal, even with several meters of shielding made of water or polyethylene, materials that are relatively good at blocking radiation. An intergalactic traveler would receive a cumulative dose that destroys bone marrow, collapses the immune system, and guarantees multiple aggressive cancers in that extra shielding. Has mass. Mass that needs to be accelerated. Mass that makes the energy problem even more impossible. Some have proposed using artificial magnetic fields to deflect charged particles, essentially recreating Earth's magnetic field around the ship. But the required fields would have to be enormous kilometers in diameter and would require massive amounts of energy to maintain continuously for millions of years, and they only protect against charged particles, gamma rays. Neutrons, other forms of uncharged radiation, would pass through any magnetic field, as if it wasn't there then. There's the problem of time. Even if we could perfectly shield you from radiation, even if we could create an impenetrable shield, intergalactic journeys, it still takes an incomprehensible amount of time. We have discussed the millions of years required. Even at relativistic speeds, and humans do not live for millions of years. We live for decades, 85. If we are lucky. The obvious solution is hibernation or cryosleep freezing, the crew putting them into some kind of metabolic stasis, waking them up upon arrival. Science fiction makes it seem simple. The reality is much more complex. We have succeeded in preserving cells, small tissues, and even some organs through cryopreservation. But a complete human, an integrated system of interdependent organs with a brain containing 86 billion neurons, each with thousands of synaptic connections, is infinitely more complex when you freeze living tissue. Water inside the cells forms ice crystals piercing the cell membranes like microscopic blades. Cells burst, tissues disintegrate. Scientists have developed cryoprotectants, chemicals that prevent ice crystal formation. They work quite well for small samples, but for a complete human body, you would need to perfuse these chemicals through every tissue, replacing all the water in every cell. And these chemicals are toxic at high concentrations. The dose needed for complete protection would probably kill you before you could be frozen, even if we solved the freezing problem. The problem of thawing is just as difficult. You need to warm the body completely uniformly if some parts heat up faster than others. The temperature gradient causes massive structural stress. Tissues crack, organs fail, and the brain, the most delicate structure of all, would be particularly vulnerable. Your memories, your personality, everything that makes you who you are is stored in the patterns of synaptic connections, incredibly fragile. Just one small error during thawing could destroy them irretrievably. And this assumes that hibernation is only done once freeze travel thaw. But on a journey of millions of years, problems will inevitably arise requiring intervention. System failures, meteoroid damage, course corrections. Someone needs to be awake to handle emergencies. That means multiple freeze-thaw cycles, each cycle accumulating more damage after tens or hundreds of cycles. Spanning millennia, the cumulative damage would likely be fatal. Alternatively, you could have a generation ship. Ships so large that an entire population lives, reproduces, and dies during the journey. The distant descendants of the original crew will finally reach the destination. But this brings a whole different set of biological problems. To maintain a viable population for millions of years, you would need perhaps at least a few thousand individuals. Any smaller population would suffer from inbreeding depression, the accumulation of harmful mutations, and eventually genetic collapse, and those thousands of people need food, water, air, living space. You need a complete, closed-loop ecosystem that can recycle every resource for millions of years without fail. Just one minor failure in water recycling or food production, and the entire population dies. Experiments with closed biosphere systems here on Earth have been consistently disappointing. Biosphere 2. The most ambitious experiment of its kind collapsed after only 2 years. Oxygen levels dropped dangerously, carbon dioxide levels soared. Species began to go extinct, and that was with only 8 people. in a relatively large and well-designed environment with Earth right outside if something went wrong. Now imagine maintaining a closed ecosystem not for 2 years, but for 2 million years. For 100,000 human generations, the probability of nothing going catastrophically wrong over that timescale is statistically indistinguishable from zero, a plague that kills a vital crop, a mutation in the recycling bacteria that makes them less efficient, a cascading failure, where one system collapse brings down others. Any one of these failures would spell the end of the entire mission. But even assuming perfect ecosystems, there is the psychological problem. Humans did not evolve to live in confined spaces. For generations, we evolved as nomads. In open spaces with distant horizons and changing skies, prolonged confinement causes depression, anxiety. Psychosis studies on nuclear submarines, Antarctic stations, high-security prisons all show the same pattern. Prolonged confinement degrades mental health even in the most stable individuals, and we are talking about confinement, not for years or decades, but for the entire lifetimes of thousands of generations, children born on a ship, living their whole lives without ever seeing a real horizon, without feeling the rain, without walking on land, and then dying, knowing their children will experience the exact same thing. The probability of social collapse, rebellion, violence is extremely high. Some psychological studies suggest that after a few generations, the population would even lose the motivation to continue the mission. Why should the distant descendants of the original crew care about reaching a destination they will never see, pursuing the dream of ancestors dead for centuries? It is likely they would eventually reject the mission change course or simply let the systems fail, because the idea of a destination has become abstract and meaningless. There is also the problem of evolution over millions of years in an artificial environment. Humans would inevitably evolve. Natural selection would favor traits adapted to the ship's environment, not the destination's environment by the time they arrived. If they ever did, they might be a completely different species. Their bodies adapted to artificial gravity. Their eyes adapted to artificial light. Their immune systems, never exposed to natural pathogens, would be unable to survive on a real planet, even if they found one. And then there is the most fundamental problem of all. Purpose intergalactic journeys would take so long that the civilization that launched them would be nothing like the civilization that benefits from them. The ships launched today would arrive in an era where humanity as we know it might no longer exist, replaced by post-humans artificial intelligences, or perhaps nothing at all, if we went extinct in the meantime. Does it make any sense to invest astronomical resources in a mission that will benefit entities so far removed from us, in time and evolution that they would essentially be aliens? Does it make any sense to condemn generations of humans to live and die en route to achieve a goal they might not even remember why it was important? Human biology is not a technical hurdle we can overcome. It is a fundamental limit, reflecting the fact that we are the product of a specific planet, evolved over millions of years to thrive, under very specific conditions. Taking us out of those conditions for cosmological timescales is not exploration. It is a form of slow extinction. Every system in your body is screaming that we were not designed for this, that our place is here on this planet under this star, protected by these magnetic fields, that the dreams of becoming intergalactic nomads are fundamentally incompatible with the reality of what we are as biological creatures. And all these biological barriers work in concert with the physical barriers we have discussed. They are not separate problems you can solve one by one. They are interlocking aspects of a single, brutal truth. The universe in its fundamental structure ensures that biological species are imprisoned. Within their home galaxies, the distances are impossible. The energies are prohibitive. Communication is severed. Space expands. Relativity imposes absolute limits, and our own fragile biology breaks down under the conditions of deep space. But perhaps there is a tiny sliver of hope in all this despair. Perhaps, if we can at least fully comprehend just how vast the universe is, how small we are on its scale, we might find a sliver of comfort, so let us explore exactly that, the brutal reality of cosmic distance, and what they really mean when you map them out with unforgiving precision. There is a reason why astronomers use terms like light years or parsecs instead of kilometers. It is not scientific pretension or needless jargon. It is because the numbers in kilometers become so absurdly large that they lose all meaning when you say Andromeda is 20 quintillion kilometers away. Your brain simply cannot process it. It is a number with no context, no scale, no emotional meaning. But when you truly understand the meaning of that distance, when you map it against what we can actually do, then the despair becomes clear. Let's start with something we can understand. The Moon is about 384,400 kilometers from Earth. Humans have been there. 12 people have walked on its surface. The trip took about 3 days with the technology of the 60s. It's far, but achievable. That's the only boundary in space we have actually crossed with our own bodies. Mars, our next target, is on average about 225 million kilometers away, about 586 times farther than the Moon. With current technology, a manned trip would take 69 months. It's challenging, but feasible. Engineers are seriously working on manned missions to Mars. We might be able to do it in the next decade or two, if we're truly committed. Now let's take the next leap, Proxima Centauri. The star nearest to our Sun is 4.24 light-years away. That's about 40 quadrillion kilometers. To put it in perspective, if the distance to the Moon were 1 centimeter on a scale model, Proxima Centauri would be over 3 kilometers away. With Voyager's technology, our fastest ship would take about 73,000 years to get there. 73,000 years? The entirety of human civilization, from the first cities in Mesopotamia until today, is only about 1/3 of that time. The most optimistic proposals for advanced propulsion, such as the breakthrough Starshot project, which plans to use solar sails, pushed by giant lasers, suggest that we could send microprobes to Proxima Centauri in about 25 years, traveling at 20% the speed of light. Microprobes, not humans, not even car-sized robots, but chips the size of your fingernail with tiny cameras. And that's the best we can currently envision, with known physics and a multi-billion-dollar investment. For a manned mission to Proxima Centauri using realistic propulsion, we're talking about journeys lasting several centuries, multiple generations living and dying along the way. And that's just to get to the nearest star, just across about 0.004% of the Milky Way's diameter. The Milky Way is about 100,000 light-years in diameter. If we wanted to travel to the other side of our own galaxy, say 80,000 light-years away, with breakthrough Starshot's technology, it would take 400,000 years. 400,000 years. Neanderthals were walking around Europe 400,000 years ago. Homo sapiens as a species has only existed for 300,000 years, and remember, that's inside our own galaxy. That's our cosmic backyard. Now let's jump into the intergalactic abyss. Andromeda is 2.5 million light-years away, about 25 times farther than the entire diameter of the Milky Way. If our entire galaxy were the size of a €1 coin, Andromeda would be over 2 meters away. And the space between the two galaxies isn't just normal empty space. It's a near-perfect vacuum, the emptiest space that exists in the universe. The density of matter in intergalactic space is about 1 atom per cubic meter. In some places, it's 1 atom per several cubic meters. That's a vacuum of a purity we could never replicate. In a lab, to reach Andromeda with Starshot technology would take 12.5 million years. From the time the first apes began to evolve in Africa until today, about 25,005 years have passed. You would need half of that entire evolutionary time to make this journey. By the time you arrived, if anything arrived at all, humanity would have evolved into something completely unrecognizable, or would have long been extinct. But Andromeda is an exception. It's part of our local group, a collection of about 54 galaxies gravitationally bound together. The local group is about 10,000,005 light-years in diameter. Inside this group, there are maybe half a dozen galaxies we could theoretically target with spacecraft. The Triangulum Galaxy, 3 million light-years away. The Magellanic Clouds, dwarf satellite galaxies of the Milky Way, are 163,000 and 200,000 light-years away, respectively. These are our cosmic neighbors, our immediate galactic family, and yet they are still incomprehensibly distant, and reaching them would require technologies that border on the limits of theoretical physics, and timescales that exceed the history of our species. Beyond the local group, the distances become truly cosmic in scale. The nearest galaxy cluster is the Virgo cluster, about 65,005 light-years away. It contains about 100 galaxies. With starshot technology, it would take 325,005 years to reach it. Dinosaurs dominated the Earth for about 165,005 years. You would need almost double that entire time period to make this trip. And the Virgo cluster is our local supercluster. Beyond it, there are other superclusters, each containing tens of thousands of galaxies, separated by cosmic voids stretching for hundreds of millions of light-years. The Coma supercluster, 330,005 light-years away. The Great Attractor, a gravitational anomaly that our local group is moving towards, is about 250,005 light-years away. The Shapley supercluster, the largest supercluster in our nearby universe, is about 650,005 light-years away. These places are so distant that the light we see left when dinosaurs still ruled the Earth, when the first mammals were mouse-sized creatures, hiding in burrows. We are seeing the deep past of those places, and reaching them would require technologies and timescales that are simply incompatible with any meaningful concept of civilization, or even a biological species. And all of this is still within the nearby universe. The observable universe has a radius of about 46,500,000,005 light-years. That's due to the expansion of space. Light from objects now at that distance has taken 13,800,000,005 years to reach us, almost the entire age of the universe. But those objects have been moving away due to expansion, while their light was traveling. But remember the Hubble horizon we discussed earlier, beyond about 4,600,000,005 light-years. Galaxies are receding faster than light can travel to reach them. About 94% of the galaxies in the observable universe lie beyond that horizon. They are observable in the sense that we can see their ancient light, but they are unreachable in any practical sense. Astronomers use something called the cosmic distance ladder to measure these vast distances. It's a hierarchy of methods, each one calibrated by the one before it. Each method extends our reach a little further. Stellar parallax for nearby stars, then Cepheid, variables for nearby galaxies, Type 1 a supernovae for cosmological distances, and each step on this ladder reveals that the universe is even vaster than the previous step suggested. There's something profoundly human in mapping the cosmos with such unblinking accuracy. It's not just that we are small, though we are. It's that we are trapped in a tiny region of an incomprehensibly vast universe, with no conceivable way of ever leaving it. It's like discovering that you live on a tiny island in an endless ocean, except this ocean is made of a deadly vacuum, and it's actively expanding to ensure you can never swim to another island. There are about 2 trillion galaxies in the observable universe. 2 trillion, each containing hundreds of billions of stars. Each star likely has planets. The number of potential worlds is so large we can't truly comprehend it. And of all those worlds, of all that potential, humanity has meaningful access to exactly one planet Earth. With extreme effort and advanced technology, maybe we could settle a few other bodies in our solar system. Mars, perhaps, maybe the moons of Jupiter or Saturn, with a lot of luck and many technological leaps. Perhaps we could send generation ships to a few nearby star systems, establishing small colonies that would probably die out or evolve into something that isn't human, and with technologies that border on the impossible, and resource commitments beyond anything our civilization has ever managed. Maybe, just maybe, we could send expeditions to other galaxies within the local group, expeditions that would take millions of years, that would be completely cut off from home, that would basically be irrelevant to the civilization that launched them. This is the map of our prison. A pale blue dot suspended in a sunbeam, as Carl Sagan called it, surrounded by a solar system we can explore in a limited way, which is inside a galaxy we could theoretically traverse in millions of years. And that galaxy floats within a local group that marks the absolute limit of any conceivable expansion. Beyond those limits, the universe continues on scales that make our largest numbers seem trivial, but for us, for any biological civilization, bound by the laws of physics, those distances might as well be infinite. They are inaccessible, not because we lack the technology, although we do, but because the fundamental laws of the universe ensure that they will forever remain out of reach. Yet, despite all this despair, despite all these insurmountable barriers, humanity continues to dream of the stars, continues to imagine warp drives and wormholes and dimensional shortcuts that allow us to bypass these limits, continues to cling to the hope that science fiction will eventually become science fact. So let's examine those hopes one by one and see if any of them can survive. An encounter with real physics for decades, science fiction has sold us a vision of the future where humanity escapes its planetary prison and expands into the cosmos. Star Trek gives us the warp drive. Star Wars gives us hyperspeed. Battlestar Galactica introduces instantaneous FTL jumps. Event Horizon seduces us with traversable wormholes. These stories are beautiful, inspiring, and full of hope. And all of it, every single bit of it, relies on physics that is either completely impossible or so profoundly unlikely that we might as well call it magic. That's not the fault of the writers. Their job is to tell exciting stories. Not to lecture on physics, but they have created generations of people who sincerely believe that intergalactic travel is just a matter of time and technological development, that eventually we will discover the trick, the loophole in the laws of the universe that will allow us to bypass these limits. So let's examine the most popular solutions from science fiction and see why. Each one falls apart when you confront it with real physics. Let's start with the most iconic one. Star Trek's warp drive. The idea is elegant. Instead of moving the ship through space, you contract space in front of you and expand space behind you. You create a space-time bubble that carries you along. As you surf on a wave of distorted space, technically, you're not moving faster than light through space. So you don't violate relativity. Space itself moves, and you go along with it. This idea is not entirely made up. In 1994, physicist Miguel Alcubierre published a paper showing that Einstein's equations of general relativity technically allow for this space-time geometry. The paper caused a lot of excitement, because it seemed we finally had a mathematical solution for faster-than-light travel that didn't overtly violate known laws. But the excitement didn't last when physicists examined the equations more closely. They discovered devastating problems. The first problem is energy to create a warp bubble, the size of a starship. The Alcubierre equations required an amount of negative energy equivalent to the mass energy of the entire planet Jupiter, negative energy. We're not talking about antimatter, which is normal matter with an opposite charge. We're talking about energy with a negative density. Something with negative pressure and repulsive gravity. Does negative energy exist? Technically, yes. There is a quantum phenomenon called the Casimir effect, which creates a tiny amount of something that acts like negative energy. Two metal plates extremely close together in a vacuum experience an attractive force due to quantum fluctuations, but the amount is ridiculously small, and no one has any idea how to amplify this to macroscopic quantities, let alone the mass energy of Jupiter. But let's assume that you could magically create negative energy. The second problem is causality. Later analyses of the Alcubierre metric showed that you would inevitably create closed, time-like curves, time loops, allowing for causality violation. You could arrive at your destination before you departed. You could be your own grandfather. The universe would be flooded with logical paradoxes breaking the fundamental coherence of reality. Physicists generally believe that there's something called the chronology protection conjecture. The universe has built-in mechanisms that prevent causality violation. The laws of physics conspire to make time machines and any technology that allows for time paradoxes impossible. If that's true, and all evidence suggests it is, then warp drives are physically impossible. Not because they violate special relativity, but because they violate something even more fundamental, the causal structure of space-time. There's also a third practical problem. Even if you could create a warp bubble, you wouldn't be able to steer it from the inside. The equations show that once you're inside the bubble, you are causally disconnected from the outside. You can't send a signal to the front to direct the bubble. You can't speed up or slow down. You can't change direction. You'd be trapped in an uncontrollable bubble sliding through space, with no way to stop or steer. Not exactly useful for navigation. All right, so warp drives are out. What about wormholes? The idea is that space-time can be bent in such a way that two distant regions are connected by a tunnel. You travel through the wormhole and instantly appear in a distant place. It's like folding a piece of paper and punching a hole. Through both layers at once, wormholes do actually appear in Einstein's equations of general relativity. They are valid mathematical solutions, but there are some catastrophic problems that make them useless for travel. First, natural wormholes, if they exist at all, would be microscopic and short-lived. They would form and collapse in an instant. On a quantum scale, to create a human traversable wormhole, you would need to stabilize it. And the only known way to stabilize a wormhole is to fill its throat with a huge amount of exotic matter. Specifically, the negative energy we already discussed again. The amount needed is astronomical, perhaps equivalent to the mass of many stars. Second, even if you could stabilize a wormhole passing through, it would be lethal. The extreme curvature of space-time at the throat would create tidal forces that would stretch you like spaghetti. You would need to make the wormhole unbelievably large for the tidal forces to be survivable, which in turn requires even more exotic energy. Third, and perhaps most devastatingly, you can't just create a wormhole. Connecting two arbitrary points in space, wormholes connect space-time regions that are already connected in some way. In the fabric of space, to create a wormhole between Earth and Andromeda, you would first need to physically drag one of the wormhole's mouths to Andromeda using conventional methods. That means the first trip still takes millions of years. The wormhole is only useful for later trips, and finally, just like warp drives, traversable wormholes inevitably allow for time travel and causality violation. If you have a traversable wormhole, you can turn it into a time machine by moving one of the ends. At relativistic speeds, this probably means the chronology protection conjecture makes them impossible. So what about hyperspace, or extra dimensions? The idea is that there are additional spatial dimensions beyond the three we experience, and by traveling through these extra dimensions you can take a shortcut. It's like walking on the surface of a sphere, versus cutting straight through the inside. Modern theoretical physics, particularly string theory, suggests that extra dimensions might exist, but there's a problem. These dimensions are compactified, curled up on themselves, at an unbelievably small scale, perhaps around the Planck length 10 to the power of -35 meters. That's about 1,000,000 trillion times smaller than a proton. These dimensions are so macroscopically small that only fundamental particles can see or interact with them. Macroscopic objects like you or a starship simply don't fit in these dimensions. It's like trying to thread a continent through the eye of a needle, smaller than 1 billion times an atom. That's not a technical limitation. It's a fundamental geometric one. Some have speculated about large extra dimensions, large enough for macroscopic objects to access them, but we have no evidence. For such dimensions and their existence would create observable effects in gravity that we don't see. Experimental tests have set increasingly strict limits on how large undetected extra dimensions can be, and those limits are now so small that they're useless for travel. All right, so what about tachyons? Hypothetical particles that travel faster than light. If they existed, perhaps you could use them for communication, or superluminal propulsion. The problem with tachyons is that they are only mathematically consistent if they never interact. With ordinary matter, the moment a tachyon interacts with something, it creates causality. Paradoxes. A tachyon could carry information into the past, allowing effects to happen before their causes. Most physicists believe that tachyons simply do not exist precisely because they would cause these causality violations. Even if they did exist, they wouldn't help you. You can't accelerate normal matter past the speed of light to turn it into a tachyon. There's an insurmountable barrier at the speed of light. Tachyons, if they exist, would be born, moving faster than light, and could never slow down below that speed. They are entirely separate classes of objects, and inaccessible from our sublight perspective. So, what about manipulating the quantum vacuum? Some speculative papers suggest that the quantum vacuum isn't truly empty, but is a sea of virtual particles constantly popping in and out of existence. Perhaps you could extract energy from the vacuum or manipulate it to create thrust. The problem is the quantum vacuum is already in its lowest possible energy state. It's like trying to extract water from a lake that's already at the lowest possible point. There's no flow of energy. You can extract the Casimir effect, which we mentioned earlier doesn't create energy from nothing. It simply redistributes the already existing zero-point energy, and the amounts are so infinitesimally small that they are completely useless for propulsion. Every proposed solution ultimately hits the same wall. The fundamental laws of physics are not laws in the sense of changeable regulations. They are descriptions of how reality works. At the most fundamental level, violating them isn't like breaking a rule. It's like trying to draw a three-sided triangle with 4 sides, or creating a married bachelor. It's a logical contradiction, not just a technical challenge. Science fiction has lied to us, not out of malice but out of narrative necessity. Stories about people being permanently trapped in a single star system are less exciting than tales of galactic empires. But the consequence of generations of these stories is that millions of people genuinely believe that intergalactic travel is inevitable, just a matter of time and progress. The truth is harder, but also more beautiful. In its own way, the universe was not designed for our convenience. It was not built for us to freely explore. The very laws that allow atoms to exist, that allow chemistry to exist, that allow life to exist, are the same laws that ensure our galactic confinement. There are no loopholes, no clever tricks, no future technological solutions. The doors are closed, not by locks we can pick, but by the fundamental mathematical laws of reality itself, and those laws do not change. They do not negotiate. They make no exceptions. So what is left for us? If intergalactic travel is impossible, if all the speculative tech of science fiction is a fantasy, if we are truly condemned to remain in our galaxy forever, what is the meaning of it all? Is this revelation a cosmic tragedy? Or could it paradoxically be the best news our species could ever receive? We have walked a dark road together. We have faced distances that defy comprehension, energy sources beyond our reach, communications broken by cosmic silence, a universe actively expanding to push our destinations away from us, relativistic limits that close all doors, biological bodies that fail under the conditions of deep space, maps that reveal our cosmic insignificance, and technological dreams that dissolve under the scrutiny of real physics. It is easy to see all this as a tragedy, as a life sentence handed down by an unfeeling universe. As the end of humanity's grand story of exploration and discovery, we go from believing we are the center of the universe to realizing we are conscious prisoners on a cosmic island, from which we can never escape. It is devastating. It is humbling. It is final. But there is another way to see this truth, a way that turns despair into something unexpectedly beautiful, because our galactic prison is not a small cramped cell, but a kingdom so vast, so rich, so filled with unsolved mysteries that we could realistically explore it. For millions of generations without ever running out of wonders, to discover the Milky Way contains around 400 billion stars. 400 billion each one, likely to have planets. Conservative estimates suggest there are at least 100 billion planets in our galaxy, and we are not talking about dead rocks floating in a vacuum. Recent exoplanet studies suggest that about 20% of sun-like stars have planets in the habitable zone, the regions where liquid water could exist. That translates to roughly 20 billion worlds that are potentially habitable in our galaxy alone. 20 billion chances to find life, to explore alien ecosystems, to find, perhaps, civilizations we could communicate with over reasonable timescales, if only 1 in 1,000 of those habitable worlds developed complex life. We would be talking about 20 million living worlds. And if only 1 in 1,000 of those developed technological intelligence, that's still 20,000 civilizations in our galaxy. We do not need to escape the Milky Way to find cosmic companions. We need to look more closely at our own neighborhood. And that neighborhood is incomprehensibly vast. Even traveling to the nearest star would take decades with advanced technology. Fully exploring just our local region of the galaxy, say, a 1,000 light-year radius, would require millions of missions over thousands of years. That is work for 1,000 civilizations for 1 million years. And this is assuming we are only interested in planets. But the Milky Way is filled with other fascinating phenomena. Nebulae where stars are born. Star-forming regions. So vast they contain enough material for millions of suns. Binary star systems where stars orbit in complex gravitational dances. Neutron stars spinning hundreds of times per second with magnetic fields so strong they distort atoms themselves. Black holes with the mass of millions or billions of suns, where the laws of physics behave in ways we are only just beginning to understand. At the center of our galaxy reigns Sagittarius, a star, a supermassive black hole with the mass of about 4 million suns. It is a natural laboratory for studying extreme gravity, relativistic physics, and the limits of our theories. Reaching it with a conventional spacecraft would take tens of thousands of years. But it is in our galaxy. It is in principle reachable. It is part of our home, and then there is the structure of the Milky Way itself. It is a barred spiral galaxy with arms extending from a dense central nucleus. It contains regions of different ages, different metallicities, different evolutionary histories, exploring how star formation differs in different parts of the galaxy. how chemical compositions evolve, how dark matter is distributed. All of these are mysteries that will take centuries of observation and exploration to solve, but perhaps the most powerful argument for accepting our galactic limits has nothing to do with what we can find out there. But what we can become here. Human history so far has been a story of constant expansion from Africa to the world, from continents to oceans, from Earth to space, and each time we reached a new limit. We overcame it. But now we have reached a limit we cannot overcome. And that forces us to do something we have never had to do before. Stop and think deeply about the kind of civilization we want to become within the limits we have for centuries. We have operated under the assumption that there would always be more territory to explore, more resources to exploit, more frontiers to cross. This mindset has led us to destroy ecosystems, deplete resources, and operate as if infinite growth were possible. But the universe has just taught us a fundamental lesson. Infinite growth is impossible. There are absolute limits etched into the fabric of reality. Accepting our galactic limits means accepting that we must learn to thrive within finite boundaries, that we must develop a sustainable civilization, not because it is more moral, but because it is physically necessary. There is no planet B in another galaxy we can escape to if we mess this one up. There is no escape from the consequences of our actions. This is liberating in a strange and paradoxical way. It removes the illusion that we can simply move on when things get tough. It forces us to fully commit to the space we have to take care of it, to build something sustainable and beautiful within our limits, and those limits are vast. I can never stress this enough. We are talking about a galaxy, 100,000 light-years in diameter, 400 billion stars, 100 billion planets. Enough material resources to build star system-sized structures, energy available from billions of stars, enough space for trillions of beings to live rich and meaningful lives, a civilization that could harness the resources of just 1% of the stars in the Milky Way would be a Type 2.5 civilization. On the Kardashev scale, controlling the energy equivalent of 1 billion suns, it could build Dyson spheres around stars, capturing every photon of energy they emit. It could build space habitats the size of planets. It could terraform worlds, create entirely new biospheres, even engineer new life forms, adapted to exotic environments. The challenges of building such a civilization would keep millions of generations busy. The coordination problems between star systems separated by light years would require new forms of governance and social organization. The ethical challenges of interacting with alien life, if we find it, would demand a wisdom we are only just beginning to develop, and there is something profoundly beautiful in the idea that we are permanently isolated from other galaxies. It means that any intelligent life that arises in the Milky Way are our cosmic cousins. We share the same galactic island. We are bound by a common destiny. To be stuck here together, we are not competitors for intergalactic resources. Because those resources are not accessible, we are potential collaborators in the project of understanding and inhabiting our shared galaxy. The impossibility of intergalactic travel also means that any intelligent life we find in the Milky Way evolved here independently of us. They are not invaders from other galaxies. They are products of the same cosmic evolutionary process that created us, that creates a foundation for empathy and understanding that would be impossible with truly alien beings from other galaxies. With completely unrelated histories, there is also a strange comfort in knowing our limits are absolute. There is no pressure to achieve the unachievable, no guilt for not conquering the unconquerable. We can relax in the certainty that we have found the ultimate limits, and within those limits, build something extraordinary. The Milky Way is not a prison, it is a perfect home, designed by the laws of physics to be the perfect size for a technological civilization large enough to contain endless diversity and mystery, small enough for interstellar communication to be possible within human lifetimes, isolated enough from other galaxies for us to develop our own unique identity without interference, and in about 4 billion years, Andromeda will collide with the Milky Way. The two galaxies will merge over billions of years in a chaotic gravitational dance, eventually forming a single giant elliptical galaxy that astronomers call Milkomeda or Lactomeda. That merged galaxy will contain about 1 trillion stars, twice the worlds to explore, twice the mysteries to solve by then. If we survive, if we thrive, if we learn to live within our limits sustainably, we will be an ancient civilization beyond imagination. We will have had 4 billion years to expand throughout the Milky Way, to seek out and potentially collaborate with other intelligent life forms to build structures and societies we cannot now imagine. And when the galaxies collide, and remember the stars are so far apart that few direct collisions will occur, we will have a whole new merged galaxy to explore, new stellar neighborhoods formed by the chaotic mixing new starburst regions where gas clouds collide, the central black holes merging into an even larger one. It's a whole new frontier that will open up automatically, without needing to violate the laws of physics. The revelation that we will never leave the Milky Way is not the end of the human story, but the beginning of a new, much deeper and more sustainable one. It is the transition from an adolescent species that believes it can conquer an infinite universe to a mature one that understands its limits and chooses to thrive within them. Limits are not prisons. When you accept them, they become the definition of home. The walls that confine us also protect us, define us, give us our identity. We are and will forever be the children of the Milky Way, born from its stardust, evolved in its light, destined to explore its mysteries for as long as we exist as a species. This is our galaxy, our home, our destiny, and it is more than enough. It is perfect, it is all we will ever need. The stars we see in the night sky are not unreachable dreams of escape. They are our distant neighbors, patiently waiting for us to grow up enough. To pay them a visit, the universe has given us a lesson in cosmic humility. It has shown us our place, not at the center, not as conquerors of an infinite cosmos, but as the conscious inhabitants of a single galactic island, delicately floating in a sea of vacuum. We will never cross, but also never need to cross, because within this island there are enough wonders for 1 million lifetimes, enough mysteries for 1 billion questions, enough space for every conceivable form of human and post-human life to flourish for millions of years. We will never leave the Milky Way, and that is not a tragedy. It is the most liberating truth our species can learn, because it means we can finally stop looking outward with envy and start looking inward with awe. We can stop dreaming of the impossible and start building the extraordinary within the possible. Our galactic prison is paradoxically the greatest freedom we could ask for, and within its absolute limits we will find not the end of our story, but its true beginning. If you've made it this far on this journey through the impossible barriers that confine us, if you've faced these hard truths without turning away, then perhaps you are ready for the next step to join those who look at the universe not with fantasies of impossible conquest, but with a deep appreciation for the extraordinary home. We already have Stay With Us on Night Science, where we will continue to explore the limits of the possible and find the beauty in the truths the universe reveals to us, no matter how harsh they may be. Yeah,